Would you take just a second and would you fill out this top right here? I asked to have those memorized. Would you go ahead and fill that out, please? So we're talking about what are the relationships among these, and then fill in the sides right here if the hypotenuse on each one of those special right triangles is 1. So this hopefully is a pretty quick process. You're going to see these over and over and over again, and if nothing else, most of you want to go to college, you're going to take the ACT. You'll see these on the ACT nearly guaranteed. So remember, on a 45, 45, 90, the two legs are exactly the same. And to go from a leg to the hypotenuse, you times by radical 2, and to go from the hypotenuse to a leg, you divide by radical 2. And on a 30, 60, 90, if you can figure out what the short leg is, you can figure out everything on there. So everything goes through the short leg, so we'll write everything with respect to that. You times by 2 to go from the short leg to the hypotenuse. You divide by 2 to go from the hypotenuse to the short leg. And then to go from the short leg to the long leg, you times by radical 3. And to go from the long leg to the short leg, you divide by radical 3. Okay? So those are the relationships there. And again, I mentioned yesterday, the way you can keep straight which one has a radical 2 and which one has a radical 3. The one that has a radical 3 in it has a 3 in the name. So the one with the 30, 60, 90's got the radical 3. Okay? And the hypotenuse and the short leg are the easy ones to find there. So if I divide by radical 2, I get 1 over radical 2. Or what do we get when we rationalize that? Radical 2 over 2, and the other one's exactly the same. The short leg's the easy one to find here, so that would just be a 1/2, and this is radical 3 over 2 once I times by radical 3. Okay? Again, really good things to have memorized. So what we're going to talk about today is something called right triangle trigonometry, and most of you have seen stuff like this before, so hopefully this looks very familiar, and we can keep this straight. So one way we can talk about trig functions is in terms of the x and y coordinate on the xy plane, and we'll do some of that. But we can also talk about the sides of a right triangle, okay? So if we figure out what angle we're going to work with on a right triangle, then we name everything else with respect to that angle. There's one side that we don't have a choice about, and it's this side right here. What do we always call this one? Hypotenuse. So I'm going to abbreviate that one as HYP, but that's the one that we don't have a choice about, so it's the hypotenuse. Okay? So the hypotenuse we don't have a choice about. And I mentioned this the other day. A lot of times this book will use the Greek letter theta to represent an angle, but we'll also use alpha and beta and gamma. But this book tends to favor theta. Now, once we name or figure out which angle we're going to work with, this has a name of the hypotenuse. The one that's across from it is called the opposite side. So I'm going to write OPP. And what name do we use for the one that's right next to it? Adjacent. So I'm going to abbreviate that ADJ. Now, opposite makes sense. It's right across from it. So it's straight across from the angle that we chose to work with. And then this one, the word adjacent, of course, means next to. Okay, so the person you're sitting next to, you could say they're adjacent to you. So you've probably learned these before, but the sine of an angle is what side over what side? Opposite over hypotenuse. Okay, cosine is adjacent over hypotenuse. And the tangent is the opposite over the adjacent. Okay? Now, you've probably learned a phrase to help you remember this. Anybody have a phrase that they use to remember the 3 basic trig functions? Brandon? Okay, SOHCAHTOA. So I didn't learn using SOHCAHTOA. My problem was I could never remember how to spell it. Okay, so you spell SOHCAHTOA, S-O-H-C-A-H and T-O-A. TOA is pretty easy, but the other two might seem a little bit weird. Okay, so SOHCAHTOA. So this says the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So if you can remember how to spell it, there's a good way to remember it. I learned this way. I learned Oscar had a hold on Arthur. Now, how would that be helpful? It's got 6 words, and we always say the 3 main trig functions, sine, cosine, and tangent. So the sine would be the opposite over the hypotenuse, the cosine would be the adjacent over the hypotenuse, and the tangent would be the opposite over the adjacent. I don't care how you remember that. In fact, I had a teacher who taught next to me in a junior high who taught it, Oscar had a hairy old ass. That's how he taught it. Ass, of course, in the biblical sense, right? So we're talking about a donkey there. Nobody ever forgot that. So there you go. Okay, I don't care how you keep those straight, but you absolutely have to keep those straight. So once we've got these figured out, we can figure out the 3 reciprocal trig functions. So remember, the cosecant and the secant and the cotangent, those are the reciprocals of each one of those. So if I wanted the cosecant, that's the reciprocal of the sine, so I'd take this and I'd flip it over. It would be the hypotenuse over the opposite. The secant is the reciprocal of the cosine, so it would be the hypotenuse over the adjacent. And the cotangent is the reciprocal of tangent, so it's going to be the adjacent on top and the opposite on the bottom. Again, you have to have those memorized. It is very hard to do trig if you don't have those basic facts memorized, the unit circle and different things like that. Okay? So you've got some problems that are like this. It says, use the triangle to find the value of all 6 trig functions. So if I've chosen this angle right here, and I've marked this side as 8 and this side as 6, I've got to figure out what the hypotenuse is. Now, this is a right triangle. What can I always use to figure out the sides of a right triangle? The Pythagorean theorem. Okay, so I can use a squared plus b squared equals c squared. These are the 2 legs, so that's going to be 6 squared plus 8 squared equals c squared. That's going to be 36 plus 64 equals c squared. And lo and behold, look what this turns out to be. This turns out to be 100, which means this side right here is 10. Now, you may recognize this. We call 6, 8, 10, we call that a Pythagorean triple. There are lots of Pythagorean triples. One that you're probably familiar is 3, 4, 5. And this is just a multiple of a 3, 4, 5 triangle. Okay? So the angle isn't a very nice angle, but the sides work out to be really nice. Now, if I'm working with this angle right here, then this would be the adjacent side, this would be the opposite, and of course that would have to be the hypotenuse. So I can figure out the sine of that angle, I can figure out the cosine of that angle, and I can figure out the tangent of that angle very quickly. So the sine is going to be the opposite, which is 8, over the hypotenuse, which is 10, which we ought to write as 4/5. The cosine would be the adjacent over the hypotenuse, so that's going to be 6 over 10, which we ought to write as the fraction 3/5. So I've got those 2 taken care of. And then the tangent is going to be the opposite over the adjacent, so that's going to be 8/6, and we definitely want to reduce that. That's going to be 4/3. Now, if I have those 3 basic trig functions, I should be able to quickly figure out what their reciprocals are. What's the cosecant then? 5/4. Just take that, flip it over. The secant would be 5/3, and the cotangent would be 3/4. Okay? And you can double check that. Let's check the cotangent. The cotangent should be the adjacent over the opposite. So if I do the adjacent 6 over the opposite 8, 6/8, I'd reduce that to 3/4. Okay, so I've got the answers right there. Any questions? Okay, Because these come up so often, we're going to run through these again. These are things that you ought to have memorized, and we'll do this over the next couple of days. Absolutely guaranteed, if you know these, you're going to do much better on the test next week, okay? So if we think about finding the sine, cosine, and tangent of 30 degrees. So if this right here is 30 degrees, we can use that special right triangle that we named up above. If this is 1, this is the short leg, so that's 1/2, and this is radical 3/2. So that means the sine is the opposite side, 1/2 over the hypotenuse, that would be 1. This is kind of the unit circle here. The cosine would be radical 3/2. And the tangent would be the opposite over the adjacent. Does anybody remember what happens when we take 1/2 and divide it by radical 3/2? You get radical 3/3 once you rationalize. Okay, so that's the right one there. If we do it for 45, so this would be radical 2 and that would be radical 2. They're both positive because we're in the first quadrant. Again, that's radical 2/2, radical 2/2. What's the tangent of 45? Piece of cake. Same number over same number, so we get a 1 right there. And then for 60 degrees, you'll notice that the triangle looks kind of like this one right here. We've just switched sides. So this is going to be, sine would be radical 3/2. The cosine is going to be 1/2. And then the tangent is going to be radical 3/2 over 1/2. And does anybody remember what we get there? Radical 3/2 over 1/2. I'm going to flip that over and I'm going to multiply. So I get 2/1. Cancel the 2's. So what do I end up with? Radical 3. Okay? Now you definitely want to have the sine and cosine memorized for each one of those angles. Tangent would be helpful. Not 100% required, but might be a good idea. So I want you to take a look at each one of these. So let's think about the sine of 30. We've got the answer right here. It's 1/2. And the cosine of 60. Cosine of 60 is 1/2. Sine of 60 is radical 3/2. And the cosine of 30 is radical 3/2. Do you want to grab that? Okay, what about the sine of 90? That's not on this list. What would the sine of 90 be? Think about where we'd be on the unit circle. Okay. Think about where we'd be on the unit circle. What's the sine of 90? 1. Okay. What's the cosine of 0? Cosine of 0 is 1. Okay. Now, clearly, these two are the same. These two are the same, and these two are the same. But what do the angles have to do with each other? Well, it's this word right here. What does complementary mean? If we say complementary angles, what happens to those angles, or what do those angles do? They equal 90 if we add them together. So it means they add to be 90 degrees. If we were in degrees, or pi halves if we were in radians. That would be complementary. So the complement of 10. What's the complement of 10? 80. What's the complement of 30? 60. Complement of 70? 20. Okay, how are you getting that every single time? I mean, those are pretty easy questions. How do you find the complement of an angle? Okay, we'll say it the right way. We take 90 and we subtract that. So to find the complement of an angle, you subtract the angle you have from 90 degrees. Or if it were in radians, what would we subtract from? We'd subtract from pi halves. So in general, if you were going to find the complement of the angle theta, how could we write down the complement of the angle theta? Like on this one, we did 90 minus 10. On this one, we did 90 minus 30. On this one, we did 90 minus 20. So how would I write down the complement of the angle theta? Pi over 2 radians minus theta. Or if we do it in degrees, 90 minus theta, or pi halves minus theta in radians. Okay? So this leads us to something that we call the cofunction identities. Okay, and it can make finding some of the trig values pretty darn quick. So we need to talk about what a cofunction is first of all. And it's kind of in the name. What do you think the cofunction is for the sine? Which one has that same name in it, but a co in front of it? Cosine, okay? So that would be the cosine of x. Sine and cosine are cofunctions. What's the cofunction for secant? Cosecant. And the cofunction for tangent is cotangent. They named them that way on purpose, okay? So if I wanted to simplify this right here, the cosine of 90 minus theta. Well, these two are complements, and they're the same. These two are complements, and they're the same. These two are complements, and they're the same. So this should be the exact same as its cofunction, which would be the sine of what angle? What would I put right here? These are cofunctions. How do these angles have to be related? How are every one of these sets of angles related here? What would it be? They add to be 90, so this is how I'd represent the complement of theta. These two are complementary, and these two are cofunctions. Okay? So if you'll flip the page over, I'm going to leave this so you can see that right there. Okay, these are called the cofunction identities. And I'm going to give you a quick way to remember these in just a second. But if I want to find the sine of 90 minus theta, that is the same as the cofunction, so that would be the cosine of its complement of theta. 90 minus theta and theta are complements. Can you see why 90 minus theta and theta are complements? What would happen if you took 90 minus theta and added theta to it? You'd get 90, so they're complementary. Okay? So this looks really weird, but all this is saying is these two are cofunctions and these two angles are complementary. So the sine of 90 minus theta is the same as the cosine of theta. The cosine of 90 minus theta is the same as the sine of theta. The tangent, what function am I going to put over here? The cotangent, and its complement would be theta. So each one of these has exactly the same structure. So this is going to be its cofunction, the tangent, of its complement theta. Secant, its complement is cofunction is cosecant, and the complement of the angle is theta. And this last one would be the secant of theta. Now, in my opinion, those are not worth memorizing. It would be much better if you memorized the idea, and you can summarize the idea with a very simple phrase. Okay, and the phrase would be this: cofunctions of complementary angles are equal. So this all may have looked a little bit weird, and this may look a little bit overwhelming to summarize or to memorize, but this phrase has all the information in it that we need. Cofunctions of complementary angles are equal. So this is a tangent of 30 and the cotangent of some other angle. What angle has to go right here? Since these are cofunctions, the angles have to be complementary, so that would be 60. Cosine of 23 would be exactly the same as the, what's its cofunction? Okay, cofunction would be sine. What's its complement? 67 degrees. Cosecant of 45 degrees would be the same as, first of all, figure out what its cofunction is. Its cofunction is secant, and what's the complement of 45? Happens to be 45, okay? Okay, degrees tend to be a little bit easier for us to work with. Now we've got to think in terms of radians. Sine of pi fourths. What's its cofunction? Cosine. And what's the complement of pi fourths? Okay, so pi halves minus pi fourths is pi fourths. Secant, what's its cofunction? Cosecant. And what is the complement of pi thirds? If you have the unit circle memorized, you can probably come up with it in a second or two. If you don't, rely on this. We're going to take 90 degrees, or pi halves, and we're going to subtract pi thirds. But then you've got to do a little fraction problem, so it would be good to have these memorized. Okay, if we're here at pi thirds, that's 60 degrees. What's its complement? 30 degrees. And what would 30 degrees be in radians? Pi 6. So if this is pi thirds right here, this is pi 6. And let's take a look at the math. This would be 3 pi 6 minus 2 pi 6 if we got a common denominator. And what do we end up with? Pi 6. Okay, you do the last one. When you get it, check with your neighbor. Cofunction would be tangent. And what's the complement to pi eighths? 3 pi eighths. 3 pi eighths. Okay? Any questions? Sure? Okay. So the cool thing about this class is if you do well in this class, you are going to breeze through 1050 and 1060. You're going to get great grades in that class, or in those two classes, and you're going to be really well prepared for calculus. Okay? So if you memorize and think about the stuff that I'm asking you to memorize and think about, I think you're going to be in great shape. The next thing we're going to introduce is something called a couple of, reciprocal identities, quotient identities, and the Pythagorean identity. You've probably seen these before if you've studied trigonometry much at all. If you haven't, these are things that you need to get used to and be very familiar with. They're things that you'd want to have memorized. So these are called the reciprocal identities. And again, we're just kind of restating a couple of facts in a few different ways. So the sine is the reciprocal of the cosecant. So the sine of theta is the same as 1 over the cosecant of theta. Its reciprocal is cosecant, so I can write this one as 1 over the sine of that same angle. So these kind of come in pairs. They are not cofunctions. They are literally reciprocals of each other. So cosine is 1 over the secant. And I say cosine is 1 over the secant. What we again say is cosine of an angle is the same as 1 over the secant of that angle. And we use theta in this case. So this would be 1 over the cosine of theta. Tangent is 1 over the cotangent. And the cotangent of theta is 1 over the tangent of theta. So if you think about it, if you've got this row right here memorized, you should have this one right here memorized, because this is the relationship between the two of them. I could just solve this one for cosecant of theta by multiplying both sides by cosecant of theta and then divide by the sine of theta. Essentially, the two of those would just switch places. Okay? So these are called the reciprocal identities. That's the relationship between each function and its reciprocal trig function. Okay? And then these are called the quotient identities. The tangent of an angle is the sine of that angle over the cosine of that angle. And the cotangent of an angle is the cosine of that angle divided by the sine of that angle. Now, I'm going to talk really briefly about why. So if I said the tangent of an angle, okay, if you flip back a couple of sections, we talked about the fact that the tangent is the y-coordinate over the x-coordinate on the unit circle, right? The sine of an angle was the y-coordinate, right? And the cosine of an angle was the x-coordinate. So if wherever there's a y, I put sine of theta, there'd be a sine of theta on the top. And wherever there's an x, I put a cosine of theta, there'd be a cosine of theta on the bottom. Sine on top, cosine on the bottom. Okay? And then this would just be the reciprocal of that. So we just take that and we flip it over. Okay? All right. Any questions there? Okay. Let's take a look at the next set. These are called Pythagorean identities. Okay, so this says the sine squared of theta plus the cosine squared of theta equals, it does equal 1. Okay, so let's talk about y. Remember on the unit circle, going all the way back to the beginning of the section, we said x squared plus y squared equals 1. That's how we described the unit circle. And going back to this right here, isn't x equal to the cosine of theta? And isn't y equal to the sine of theta? So if I put a cosine right here, this would be the cosine of theta squared plus the sine of theta squared. That should equal 1 also. So this would be the cosine squared of theta plus sine squared of theta equals 1. And does it matter whether I write cosine first or second? It doesn't, because of the commutative property of addition. I can move things around in an addition problem and it doesn't change the answer. So this is called the Pythagorean identity. So if we said we're talking about the Pythagorean identity, that's the one we're talking about. Okay? You don't have to wonder. In fact, some books will call this the fundamental trig identity. Okay? So that's one that you've got to have memorized. Now we're going to take a look at this and we're going to change just slightly. I'm going to take this one and I'm going to manipulate it just a little bit. Okay, I'm going to take this one, and in blue, I'm going to divide every single term on both sides by sine squared of theta. Now again, just to point out, when we write down, I'll write it down here, when I write sine squared of theta, it doesn't mean take the sine, square it, and then plug the angle in. It literally means this. We're taking the sine of an angle, and then we're squaring that. We just write it here. We don't write the parentheses. It's a little, remember, mathematicians are a little bit lazy. This is just the shorthand that we use to write that. Okay? So find the sine of the angle and then square it. What if I have sine squared over sine squared? What would that be equivalent to? A 1. Cosine squared over sine squared. What is cosine over sine? That's going to be cotangent. So this is going to be cotangent squared of theta. And what is 1 over sine squared, or 1 over the sine of an angle, quantity squared? Does anybody recognize that? Cosecant. It's the cosecant. So this would be cosecant squared of theta. Okay, does everybody see how we went from the Pythagorean identity to this kind of adjustment, this new version of the Pythagorean identity that involves cotangent and cosecant? Any questions there? Okay, I'm going to change colors again then, and we're going to come back here, and instead of dividing by sine squared, I'm going to divide by cosine squared of theta. So as long as I'm doing the same thing to both sides, it shouldn't change the validity of the equation. What is sine squared over cosine squared? Sine squared over cosine would be tangent, so this is going to be tangent squared of theta. Cosine squared over cosine squared? That's a 1, so we'll put a plus 1 here. And then on the other side, it's going to equal 1 over cosine squared. 1 over cosine is secant. So this is going to be secant squared theta. Again, if you've seen these before, hopefully these look familiar. If you haven't, again, I just emphasize that when we write something like this, we literally mean find the secant of that angle and then square it. Find the tangent of that angle and then square it. We just, by convention, we don't write the set of parentheses. We just slide that square over there. Okay, any questions? Sure? Raise your hand if you've seen those before. Okay, about half of you. So the other half have probably quite a bit of work to do. Okay, so let's take a look at example number 5. It says, suppose we know that the cosine of theta is equal to 0.8, and theta is an acute angle. Use identities to find the sine of theta, the tangent of theta, and the secant of theta. Okay, well, one of these is really easy to find. And it does say use identities. Of these three, which one would be the easiest to find? Secant. Because what would we do with this? We'd flip it over, wouldn't we? Okay, so this is going to be 1 over the cosine of that angle, so that's going to be 1 over 0.8. Go ahead and grab your calculator if you need to. So if I were to type in 1 divided by 0.8, I end up with 1.25. And because the problem was written as decimals, I can go ahead and write this as 1.25, and I've got that answer right there. So the secant of theta is equal to 1.25. I want to find the sine of theta. Well, what I'd look for is something up here where I've got an identity that involves both the cosine, which I know, and the sine, which I don't. Is there an identity up here that has a cosine in it and a sine in it, and the rest are just numbers? Yep, right here, right? Okay, so I'm going to say sine squared theta plus, what's the cosine of theta? 0.8. We'll square that, and that's going to equal 1. So I'm using this equation right here. Remember, an identity is just a true equation. I don't know the sine squared. That's what I'm trying to find. Or I don't know the sine. That's what I'm trying to find. So I have sine squared. I do know the cosine, so I plug that in. This goes from having 2 variables in it to just having 1. So I'd move this over to the other side. So this is going to be the sine squared of theta equals 1 minus, this would be 0.64, correct me if I'm wrong. So this is going to be sine squared theta equals, this would be 0.36. And then how do I figure out what the sine of theta is? Take the square root of both sides. That will undo the squaring, so I get the sine of theta equals, now do I need a plus or minus on this one? I don't. It's going to be the positive one because we're talking about right triangle trigonometry. We're talking about positive side lengths, and it says it's acute. It would be in the first quadrant, so they'd both be positive. This is 0.6, isn't it? Okay, now I've got one last one to find. I need to find the tangent of theta. Is there an identity up here in our list that we should get memorized where if I know the secant and the cosine and the sine, I can figure out the tangent? I could use any one of these 3 guys right here in order to figure it out. Okay. I could do a couple of things. I could use this one right here, couldn't I? If I want to find the tangent and I know the secant, couldn't I use this one? Or is there an easier one? The quotient one. The tangent of an angle is the sine of that angle, which is 0.8, over the cosine of that angle, which is 0.6, which if you take a good look at that is going to be, well, let's see, isn't that going to be like 1.3? Oh, I wrote that down wrong, didn't I? 0.6 on the top and 0.8 on the bottom. So this is going to be 3/4 or 0.75. Okay. Any questions? Okay, let's take a look at the next couple then, and then hopefully, well, we might be able to finish this up. Okay, so on example 6 it says the sine of an angle is 5/13 and alpha is in quadrant 1. Can you find the values of the other trig functions using identities? Okay, now, we could draw a picture of this, and we'll get to that, but this says use identities. Okay, and you'll have some problems on the test that will say use identities in order to figure these out. So let's go through and let's figure this out. If I know the sine, what other one is the easiest of the other 6 to find? It's reciprocal, the cosecant, right? So that means that the cosecant of alpha is equal to 13/5. So I've got that one taken care of. And I'm going to circle this one also. Okay? So I've got 2 of the 6 taken care of. What one should we find next? If you had to name your 2 favorite trig functions, say you're a complete math nerd and you actually have 2 favorite trig functions, what 2 would they be? Probably sine and cosine, because you can write all the other ones in terms of sine and cosine. So if I have the sine, let's figure out the cosine. So let's use the fundamental trig identity, this Pythagorean identity. This is going to be 5/13 squared for the sine, plus cosine squared of alpha equals 1. Now notice here it was written with thetas. Here I've changed the angle to alpha, no problem with that. So that means cosine squared of alpha is going to be equal to 1 minus, I'm going to move that to the other side and I'm going to square it at the same time. This is going to be 25 and this is going to be 169. Get a common denominator. This would be 169 over 169 minus 25 over 169. And can somebody tell me something nice about that little fraction problem? The bottom's still 169. What's the numerator? 169 minus 25. 144. What's nice about that fraction? They're both perfect squares. They're both perfect squares. So when I take the square root, I get this. I get the cosine of alpha is equal to square root of 144 is 12, and the square root of 169 is 13. So I get some nice numbers. So I've got 3 of them taken care of so far. But if I've got the cosine, what other one can I find just like that? It's reciprocal, the secant. So the secant of alpha is going to be 13 over 12. And really, if I've got the sine and the cosine, I've pretty much got everything else figured out, right? So the tangent of that angle is going to be the sine 5/13 over the cosine 12/13. And again, what's cool about this is if I flip this over and I multiply, that's going to be a 13 on the top and a 12 on the bottom. So that means that the tangent of that angle is equal to 5/12. And if I've got that one, I've got its reciprocal, the cotangent, 12/5. Didn't draw any pictures, just relied on the identities to figure those out. Okay, are there any questions? Sure? Not the funnest thing on the planet, but do you get it? Or maybe it is really fun. I do this on weekends. Yeah. It's fun for you? Okay. All right. So let's take a look at example number 7, and then we'll just do as many of these as we can before we leave, and we'll pick it up tomorrow. Okay? So are the following identities? Okay, now remember, what's an identity again? A true equation. So is this a true equation? Yeah. Sure. Because we took the 5/13 over 12/13. I flipped the denominator over. This is a complex fraction. So the 13's canceled, so that leaves a 5 on the top and a 12 on the bottom. Good question. Anything else? Okay, so the question here is this a true equation? Does the sine of an angle times the cosecant of an angle, does that equal 1? Well, the way we'd verify this is maybe if we wrote everything in terms of sines and cosines, that would make a little bit more sense. What is the cosecant? It's the reciprocal of the sine, right? What's the sine of alpha times 1 over the sine of alpha? So does this side equal that side? Yes, it does. So the answer there is a yes. Okay? That is an identity. If you take the sine of an angle and multiply it by the cosecant of an angle, you always end up with a 1. Let's take a look at this one right here. The sine of an angle times the cotangent of an angle is the cosine of that angle. So gosh, it would be a lot easier to figure this out than it would be to figure the two of these out. So is this true? If you take the sine of an angle, and what can I put in place of the cotangent of alpha? Cosine of alpha over sine of alpha. Cancel these off, I get the cosine of alpha. So yes, that's an identity. Okay, that's a true equation. Any questions? Okay, you've got enough information that you could do most of the problems on the assignment. I do want to take a quick look at each one of these right here and just talk about them, and if you can figure them out on your own, great. We'll talk about them real briefly tomorrow at the beginning of class, and then we'll start section 4.4. So if we look at this problem right here, it says, what could be figured out from the following diagrams? So if I know this angle of elevation right here is 71.5 degrees, and I know that I'm 50 feet away from this tree when I take that measurement, what are we trying to find here? Trying to find how tall the tree is, right? Is that a right triangle? So if I drew that right triangle over here, and I said this is 50, and that's a right angle, and this is 71.5 degrees, and I want to find this right here, I have this angle. What side would I name this? Opposite. What side do I have? I have the adjacent. So I'm looking for the opposite, and I have the adjacent. What trig function relates the opposite and the adjacent? The tangent does. So that means the tangent of that angle, 71.5 degrees, should equal the opposite, which is y, over the adjacent, which is 50. Could we take that and solve that for what y is? Sure. Times both sides by 50. You'd need a calculator to get the actual answer. By the way, do you expect an answer for y that's bigger or smaller than 50? Bigger. Why? How come? Because this side's longer, because this is, it's bigger than 45. That's going to make the opposite side bigger than the adjacent side. Okay? What question might they ask on this one right here? They might ask us how far it is from there to there. What could you use for that? Guess you could just use the Pythagorean theorem. Or maybe they ask you what that angle is. Maybe we're not sure what that angle is. And on that one right there, does that look like there's very much information there? There's not. Just the picture would not be enough to solve that. You'll notice that on this one we had an angle and a side. On this one we've got two sides. We've got two pieces of information. How many pieces of information do we have here? Only one. Tough to solve a problem like that with only one. I'll add information to that so we can solve that. Okay? That's it for today. You can go ahead and get started, but don't consider 4.3 officially assigned today. But I would go ahead and get started on it. Okay? Especially if you're done with 4.2.